Okay, so as I was saying, glycolysis is the breaking up of the sugar. Okay, again, it takes place in the cytoplasm, and the typical sugar that we look at is glucose. And the reason that we look at glucose is because typically all organisms, whether it's a bacteria or cells, we all can catabolize glucose. That is not true of all other sugars. So if you want to show the glycolytic pathway, we typically talk about glucose, okay? So glucose is a 6-carbon sugar, okay? And what we're going to do is we're going to break it, we're going to lyse it in half and produce 2 3-carbon sugars that are high in energy. How high in energy? So high in energy that they can actually carry out this event called substrate level phosphorylation, which means that the intermediate is high enough energy to transfer an inorganic phosphate to adenosine diphosphate and make ATP, adenosine triphosphate. There's also the production of some NADH. So let's take a look at this. Okay, it looks like this. All right. And I got to tell you that this is what the author gave us in the PowerPoint. And I find it amusing because it's wrong, okay? If you notice here, I'm going to enlarge this so you can see a little bit better. But if you notice here, we're starting with that sugar that we're talking about. Is a glucose with 1, 2, 3, 4, 5, 6 carbons, okay? And we go through some what's called energy investment. Anyway, anytime that you invest a phosphate, you're investing energy. So you've heard the old axiom, it takes money to make money. Well, apparently it takes energy to make energy. So in glycolysis, we invest energy before we harvest energy. And as we go through these first steps, we go through the glycolytic pathway where we take this sugar and we break it in half, and we end up with not 1, but 2 3-carbon sugars down here. So this thing that we're looking at, this arrow should go down only one side. You should ignore the other side. It's a mistake by the author. All I can do is blanket out one side, but it's been like that for about at least the last 2 editions. So anyways, what do we have going on? We have a glucose. We're going to invest some energy, okay? So you can see it happening here. Oops, my apologies. You can see it happening here. We're investing energy by putting a phosphate group. And in case you don't understand what's going on here, a phosphate group is a large negative group, okay? So imagine that you have a chain of 6 carbons and your goal is to break them apart. What do? Well, one thing you can do is you can put a large magnet on one side and a large magnet on the other side so that both norths are facing each other and therefore they want to repel. And then if you take some scissors in the middle, those magnets are going to repel and they're going to pull those sugars away from each other. Well, that's exactly what's happening here. This phosphate group right here is very large and very negative. So we're putting one on one end, then we're putting one on the other end. So effectively we have 2 large negative charges that just want to tear away from each other. And then an enzyme comes in here and cuts this guy in half. You end up with 2 sugars, okay? So that's great. So what happened? We had to invest energy. How much? 1, 2 ATPs, all right? Now what? Well, now we have these 2 high energy intermediates. How do we know that they're high energy? We know that they're high energy intermediates because this shuttle here, this NAD, is harvesting high energy electrons, okay? And the only way that that can happen is if these precursors right here were high energy. So notice that we have 2 NADs. This is a little shuttle, okay? It's a low taxi cab. And this taxi cab, what it's picking up is powerful electrons, high energy electrons. How many of them? 2 of them. Okay? Now look at what's going on next. Now, these guys are still very high energy. How do we know? Because we are having what's called substrate level phosphorylation. In other words, we're taking 2 ATPs and we're turning them into ATP. So ATP is low energy, ATP is very high energy, okay? And we're going from low energy to high energy in order to produce this desirable currency of energy, which is the ATP. Now, it doesn't happen once, it happens twice. Do you see that? Okay? So, let's look at the big picture. Okay? Let's look at the big picture. What's happening? We invest 2 ATPs of energy. That's a loss. Then we harvest 2 NADHs. That's a win. And then we're going to harvest 2 plus 2, 4 ATPs. Those are a win. Are you guys with me? So let's do some accounting. Here's my accounting. Okay, here's my accounting Excel spreadsheet. And what we're going to do is we're going to keep track of this. So in glycolysis, how much ATP do we make? Well, we made 2 plus 2. We made 4. But we had to invest 2 for the glycolytic pathway. So 4 minus 2 is 2. So at the end of the day, we only made 2 ATP in glycolysis. Okay. What about NADH? Did we make NADH? Well, we did, right there. How much did we make? Well, we made 2 of them. Yay! Did we make any FADH? No, not at all. Did any carbon dioxide come out of it? No, not at all. So there we are. That's glycolysis. Okay. So far, what have we done? Due to glycolysis, we have been able to, here, let me get very specific with my spreadsheets. There we go. Thanks to glycolysis, we have made 2 ATP and 2 NADH. These are 2 different types of energy. Okay. Now what do we do? Well, now we're going to go to the next step. Okay. So remember, in glycolysis, okay, there's an energy investment stage of 2 ATPs and an energy, I call it energy harvest. I don't know what energy conserving is. Energy harvest phase where we harvest 4 ATP. Okay. 4 minus 2 is 2. And so the net amount of ATP is 2 ATP. Okay, we're doing great. Let's keep on going. So now what we're going to do is we're going to make the synthesis of acetyl-CoA. Oh, I almost forgot something. What's the product of glycolysis? Well, if you look at your low power point here, okay, if you look at your low power point here, at the very bottom, we notice that at the end of the sugar, we end up with 2 3-carbon groups, which is called pyruvic acid. That is the end product of glycolysis. 2 pyruvic acids for every sugar that comes in. Okay. All right. Let's go to the intermediate, to the synthesis stage. So we're going to go to the second step. Now, this synthesis of acetyl-CoA takes place as the pyruvic acid enters the mitochondrial matrix in eukaryotic cells such as us. In prokaryotic cells, it doesn't need to go into a compartment. It just stays in the cytosol. Okay, so we're going to go through this. So what does that look like? Well, it looks like this. Here's a pyruvic acid from glycolysis, and this beautiful enzyme by the name of pyruvic acid dehydrogenase carries all this out. Okay, what does it do? It decarboxylates the pyruvic acid. In other words, it takes out a CO2. For you and me, what that means is that there's no energy in that CO2. All the energy, all biological energy has been harvested. Nothing else can be done from there. So we're going to take away this waste, this decarboxylation. Okay, when that happens, this moiety over here of the pyruvic acid was left as acetate. Then that acetate joins that to an arm, okay, which is called coenzyme A. And when that acetyl group, acetate, associates with a coenzyme A, it's called an acetyl coenzyme A. But in doing that, we also look at this beautiful thing. We harvest high energy electrons. Again, anytime that you see NAD turning into NADH or FAD turning into FADH, that's high energy harvest. So here's a harvesting of high energy electrons, okay? So let's go back to our Excel. Here's Excel. Here's the synthesis of acetyl-CoA. How much ATP do we make? Well, the short answer is we didn't make any. Okay. How much NADH did we make? Well, if you look here, it looks like we made one. But remember, here we're accounting for a sugar. And each sugar makes 2 pyruvic acids. So if each pyruvic acid makes 1 NADH, then each sugar makes 2 NADHs. So we're going to put a 2 right there. How many FADHs? None. We didn't make any. Too bad. How much carbon dioxide? Well, apparently we got rid of 1 here. See that? But remember, that's per pyruvic acid. So 1 per pyruvic acid, that's equal to 2 CO2s. So we're going to put a 2 right there. Okay. And I'm going to stop here because I think that my recordings, the longer that they are, the harder that they are to put up. So I'm going to stop here and then make another one, okay? So I'll see you in a little bit.